Hi everyone, Mr. Smith here, and in this lesson we are talking about gravitational fields and gravitational field strength. So let's get started. We're going to dive right in. What is a gravitational field? Well, gravitational field exists in the space surrounding an object in which the force of gravity exists. So basically, anything with mass will set up some kind of a gravitational field around it, where if you put another mass in that field, it's going to feel some kind of gravitational force, according to Newton's law of gravitation. And gravitational field strength increases when you have more mass. So the field strength around the sun is greater than the field strength around Earth because there's more mass. And it decreases the farther you get from that object. So, for example, the farther you get away from Earth, the gravitational force you feel isn't as strong. We know that from Newton's law of gravitation. Here's a little visual, a 2D diagram of a gravitational field. So this is you might call this a field line diagram. And so the first thing to note is that in this diagram of a gravitational field, the field lines indicate the direction that an object would accelerate, or kind of the direction that the force would be in. So these lines here, these arrows, these are called field lines. So those indicate the direction, and no surprise here, you can see that the field lines all point towards the mass setting up the gravitational field, because we know that any mass would be attracted to that mass setting up the field. So the direction of the field lines makes sense. It tells you which way the force would be or which way an object would accelerate. And the second thing is that the more tightly clustered the field lines are, the stronger the field strength. So you can see around the mass itself how the field lines, it's very dense, right? They're all like tightly packed together. It means the field strength is stronger. And the farther you get away, the field strength lessens. And you can see these guys here are more spread out around the farther you get from the mass. Here's a few more field diagrams, and I wanted to use this to illustrate why, for our purposes in grade 11, like analyzing roller coasters and like pole vaulters, we don't really need to consider that the gravitational field around the Earth might be changing. So figure 1C actually shows you, kind of treats the Earth as a point mass, and you can see the comparison between the field lines for this diagram here and for treating the Earth as kind of a point mass. So that kind of makes sense, and you can see that, it's closer to Earth, the field lines are tighter together, farther away, they spread far apart. But as you zoom in with figure 1B and figure 1A, the more you zoom in, the harder it is to tell that these field lines are kind of more spread apart. And actually, when you get right up to, say, the surface of the Earth, where for us that surface appears perfectly flat, those field lines, as far as we're concerned, are basically parallel. We can't really see the curvature of the Earth like on a scale like figure 1A. And so we're seeing those field lines all point towards like straight down, and they're all parallel. So that's why in our grade 11 course, we just said, okay, you know what? Gravitational field strength is the same everywhere. G is the same everywhere. We can kind of blissfully ignore that field strength changes the farther away you are from the mass. What's also interesting too is that things are even more complicated because we won't dive into this level of detail, but the Earth is not a perfect sphere, and nor is the mass of the Earth uniformly distributed. It's not like a perfect like little marble with like a perfect density that's constant all the way through. You have more dense regions of Earth, you have less dense regions of Earth. So what figure 1D illustrates is, say you had some region of Earth that was very, very, very dense and had a lot of mass. Off the top of my head, I don't really know what like the most massive like materials are, but maybe some big iron deposit or something like that, very massive. That kind of affects the gravitational fields in little minute ways. So This visual in figure 1C is a very, very general, and for our purposes, it works fine, but a very general idea of gravitational fields. In reality, mass distribution, mountain ranges, like all kinds of things play into gravitational field strength. But we're going to keep things simple. We're going to just imagine the gravitational field set up by some kind of point mass, like the Earth. So right now, we're going to actually make a derivation for gravitational field strength. So we're going to let G represent the acceleration due to gravity of some distance r away from mass m. And when I say some distance r, that is the center to center separation, just like we've been using in Newton's law of gravitation. So our starting point will be the following. We're going to start with just sum of forces, Newton's second law, equals mass times acceleration. Now, we are saying that g is our acceleration due to gravity. So in all of our problems near the Earth's surface, we're using Fg equals mg, because we just say g is just the acceleration at the Earth's surface. It's 9.8. Well, now I'm going to replace a with just a more general. I'm just going to replace that with g. So g is acceleration due to gravity, and we actually know this force now, right? This gravitational force, Newton's law of gravitation, G big M over little m, G big M little m all over r squared. And what you'll notice is, if we look at the two sides of this equation, each have a little m. And we get an expression for gravitational field strength, G, or our acceleration due to gravity, and we'll talk about the connection there in a second, in terms of the mass of the planet or whatever this body is, divided by how far you are away. So this is our new derivation, our formula for what we call gravitational field strength. In that formula, G is just G, our Newton's constant, the gravitational constant. M is the mass of the body setting up the field. So if we're doing a problem around Earth, we're considering big M to be the Earth's mass. But if we're doing a problem, say, on looking at a satellite orbiting Mars, then we're going to be talking about Mars's mass. And R, just to stress that, I'll use caps, all caps. I'm shouting center to center separation. So it's not the distance, say, above a planet. It's the distance from these to the center of that planet. We're kind of treating it as a point mass. So this is gravitational field strength, and I have a few notes here. The units of gravitational field strength are newtons per kilogram. They're equivalent to meters per second squared. Just going to erase that. The gravitational force on an object is equal to mass times this gravitational field strength. And if you rearrange that, this gravitational field strength is equal to gravitational force divided by mass. And what we have seen is that equals to G big M over r squared. So you can see this gravitational field strength, or acceleration due to gravity, is the gravitational force divided by the mass in the field. And so you get newtons per kilogram. And newtons per kilogram are equivalent to meters per second squared. Just do a small analysis at the side here. So just think newtons per kilogram. Remember, the newton is the kilogram meter per second squared. And if you're dividing by kilograms, squeeze that in over here, you just get meters per second squared. The next little concept to mention. So this gravitational field strength, I just want to say it is a vector. So the formula gm over r squared gives its magnitude. And just like gravitational force is always an attractive force, this is always towards the center of mass of the body setting up the field. Now, we talked about these units being newtons per kilogram. So what this means, so if G is 9.8 newtons per kilogram, this means an object would experience 1 newton of force for every 1 kilogram of mass. And, in the same way, I'll say also, an object would accelerate at 9.8 meters per second squared. So those two things are equivalent. So we've been using G as our acceleration due to gravity. More generally, it's called gravitational field strength, and it actually depends on the mass of the body and how far away from you are from its center. These two things mean the same thing. 9.8 newtons per kilogram, an object would experience 1 newton of force for every 1 kilogram of mass. But that 9.8 value also means an object would accelerate at 9.8 meters per second squared. Those two statements are kind of equivalent. So let's actually just get calculating some gravitational field strength. So our formula is for the field strength. So we understand the gravitational field direction is always towards the center. So we're using this our derived formula. So yeah, let's just give that a try. So you're going to need your solar system data. So maybe you printed that off, or maybe you want to head to Brightspace and just pull that up. I have it up too. But what is the gravitational field strength on the surface of the sun? And just for this question, I'm going to emphasize that it's like the mass of the body setting up the field divided by r squared. And so here, if we're on the surface of the sun, then r is just going to be the radius of the sun pretty much. So we have 6.67 times 10 to the negative 11. Mass of the sun, 1.99 times 10 to the 30. I use that one enough that I have it memorized. Radius of the sun, not so much. So I have it up here. Radius of object, 6.96 times 10 to the 8. And we're in kilograms, we're in meters, so we are going to get our final answer in SI units. (30) divided by 6.96 x 8. Oh, and don't forget to square it. That was naughty there. Squared. So I got about 274. And when asked for gravitational field strength, often we say it's newtons per kilogram. But if you were to say 274 meters per second squared, that would be fine too, which is crazy that an object at the surface of the sun would experience an acceleration of 274 meters per second squared. This also means every kilogram of your mass, for every kilogram of mass you have, you'd experience 274 newtons of force. You'd absolutely be crushed. Just to compare, let's just compare if you take the gravitational field strength for the sun and divide it by the gravitational field strength for the Earth. So that's 274 newtons per kilogram divided by 9.8 newtons per kilogram. I mean, it's like 28, right? 20 or 29? It's 28. So you would feel 28 times heavier on the surface of the sun. You'd be crushed by your own weight. So pretty interesting. Let's just play around this a bit more. We've talked about how G, gravitational field strength, and acceleration due to gravity are affected by how far you are away from the center of whatever body is setting up the field. Well, the Earth is not a perfect sphere. It's what we call an oblate spheroid. And so the distance from the Earth's equator to the center of the Earth's mass is different from the the North Pole. I have these values right beside me. I do not have these memorized, and I'm not going to have you guys look these up. But at the equator, kind of that maximum R, that distance is 6,384 kilometers. And for the Earth's North Pole, we'll use 6,353 kilometers. So it looks like a 31 kilometer difference. And, you know, in our classic, all of our applications, we're usually using G equals 9.8, or if we have three significant figures, we're using 9.81. So let's see how well those estimates hold up at these two extremes. So here we're talking about the Earth, right? The Earth is setting up the field, and so we're using the mass of the Earth. So 6.67 times 10 to the negative 11, mass of the Earth. I probably should have the mass of the Earth memorized at this point. 5.98 times 10 to the 24. I knew that. And we are using, so 6,384 kilometers is 6,384,000 meters. And we're squaring that. And then while you guys calculate that, I'll set up my next one. So we'll be doing G, mass of the Earth. And this time, 6353000 squared. Let's see how much of a difference it makes. Are we kind of justified in just using like 9.8 all the time? Well, let's see. 5.98 is 24 divided by 6384123. So I got 9.79 newtons per kilogram. So yeah, 9.8 seems pretty good. At the North Pole, 6.67, 11 times 5.98, x24. So we are a little bit closer to the Earth's center at the North Pole. That distance is not as big, so we should get a larger value for G. Let's find out. 6353. Crazy. 9.88 newtons per kilogram. Now, of course, we have mountain ranges. We have places below sea level. Obviously, those distances can change, but it kind of gives you a perspective on how, even just on the Earth's surface, that using G equals 9.8 or 9.81, isn't perfect. You can see the fluctuation here. So that's a pretty cool example. So we've just done a couple examples, finding out what that acceleration due to gravity is, or this gravitational field strength. Let's compare field strength for between Earth and Mars. And then we might just have a look at the other planets and what their gravitational field strengths are, just for fun. So, another pen here. But you guys should be pros at this now. For finding the field strength on the surface of Mars, we are using the mass of Mars and the radius of Mars. I do not know the mass of Mars. It is 6.37 times 10 to the 23. So not as massive as Earth. And its radius, the radius of object of Mars, 3.4 times 10 to the 6. Don't forget to square it when finding gravitational field strength. So right away we can see, well, Mars is not as big, not as massive, and it's smaller in radius. So we're definitely expecting a smaller gravitational field strength. But how much? Let's find out. Divided by 3.4x6 squared. So about 3.7 newtons per kilogram. So if you compare that to, so that's part A. So if you compare that to Earth, do a little ratio. Actually, let's do Mars on top. G Mars over G Earth, about 3.7 newtons per kilogram divided by 9.8 newtons per kilogram. So in terms of Earth's gravitational field, 3.7 divided by 9.8, it's roughly, that's 0.38. So it's like 38% of Earth's gravitational field strength. So not insignificant, but you're not going to feel your normal weight on the surface of Mars. You'll definitely have a little bit of hop to your step. You'll definitely feel a bit lighter. So that's interesting. And consider the following table. It has data for the other planets as well. So we just did the ratio for Mars, and we got about 0.38 or 0.37. 0.38. We did a bit of rounding though. So the gravitational field strength for Mars, about 37.5% of what it is for Earth. And you have some other comparisons too. For Mercury, it's about the same, 37.5. For Venus, about 0.9, so very close to Earth gravity. Jupiter, 2.5 times. Saturn, very close. Uranus, very close. Neptune, very close. But if you look at Pluto, 0.067. That's like 7% of Earth's gravity. And so this is kind of one argument for why Pluto was kind of like declassified as a planet, because its gravitational field strength is just not very, it's just not very much. In fact, when you compare it to the moons, now the moons was not, we didn't find that, it's not listed here, but the gravitational for the field strength for the moon over for the Earth. So the moon's is about 1.6 newtons per kilogram, and Earth's is about 9.8. 1.6 divided by 9.8 is 0.16. So the moon has a gravitational field strength on the surface of like 16% that of Earth. Pluto is 7%. So very loosely speaking, but gravity is stronger on the surface of the moon than on Pluto. So why are we calling Pluto a planet? I don't have a stake in the game one way or the other. I don't really care if Pluto's a planet or not. But I just found that interesting to share with you guys. So that concludes our lesson, maybe a little bit of a mini lesson on gravitational field strength. So hopefully you guys saw the connections between that and acceleration due to gravity. This idea of we've been using G as acceleration due to gravity. We're now also thinking about G as gravitational field strength, newtons per kilogram. And remember, they are the same thing. What's coming up next? So now that we know that G changes as you move farther away from a planet or body, we need to update how we do gravitational potential energy, because MGH just doesn't cut it anymore if G is changing and is not constant. So in our next lesson, we're going to derive a new formula, not rederive, we're going to derive a new formula for gravitational potential energy for distances that are large. So it should be a lot of fun, actually. Right, guys, that's it for this lesson. Hope you're staying well. Have a great day. We'll see you soon.